All right, welcome back to this channel. Based on the request from one of the students that said you didn't understand this topic of density, I'm going to be I'm going to be teaching density again, and this time I'm going to break it down better. Is that okay? I'm going to be solving up to. He sent some 5 questions to me. Okay, so those 5 questions, I'm going to use them in explaining the concept of density. Now, let's start again from definition. What is density? Density, first, it is denoted by rho. This is a Greek letter, rho. Is that okay? And don't confuse it for resistivity. In fluid mechanics, rho means density. In electricity, rho means resistivity. Okay. Now, I said, what is density? Density is given as the mass per unit volume of a substance. The density of a substance is the mass of that substance per unit of its volume. I'm going to explain what that means. For example, the density of water is experimentally found to be approximately 1,000 kilograms per meter cube. What this first means is that the density of a substance, which is the mass per unit volume of that substance, means that if I take any unit of volume, for example, what is volume? Volume is what? Length times breadth times height, right? So if I take length times breadth times height using either centimeters, you know standard unit is meter, right? Standard international unit. So, but if I use centimeter or meter, any particular unit that I use, so one volume, according to that unit, the mass of one volume. So if the unit is centimeter cube, that is the mass of 1 centimeter cube of the substance. That's the density of that substance. Or the mass of 1 meter cube of a substance. That is the mass of what? Of that substance. Okay. So that's the density of that substance rather. So what this means basically is this, that the density of water is 1,000 kilograms per meter cube. It means that if I can get a particular container that is exactly 1 meter by 1 meter by 1 meter, that is a cube, right? Yeah, something like this, and I fill it up. Oh God. And I fill it up with water. So you know that this is a cube. Basically, all of the surfaces are sphere. They are squares rather. So we have 1 meter here, 1 meter here, 1 meter all around. Is that okay? So by the time I'm taking the volume is going to be what? Length times breadth times height. Is that okay? And that will give you what? 1 meter cube. Is that okay? So it means that if I weigh the water inside here, the water will be exactly 1,000 kilograms. That is, if I weigh the water that I can pour in a container that is 1 meter by 1 meter by 1 meter, if I were to weigh it, the mass will be 1,000 kilograms. Okay. So that is the meaning of density. That is the mass of 1 unit volume of a substance. I repeat, the mass is not weight, you know that, okay? But think of it as, that's how to think of it as heavy, even though we know that the mass is the quantity of matter that something consists, okay? So, but think of it as weight, so how heavy, kind of. So, because the more the mass, usually, the higher the weight. Does that make sense? Okay, so the volume, the density of a substance will be the mass of 1 unit volume, say 1 centimeter cube, say 1 meter cube, say 1 dm cube, say 1 millimeter cube of a substance. The mass of that 1 unit volume is going to be the density of that substance. I believe that is clear. So now I have this as the definition of density. Now, the first scientists to work on density, or that principally worked on density and came out with, with good finding, with, very, came out with propositions and postulates. His name is Archimedes. And you see, Archimedes postulated a law. That day we were working together actually in his lab. So, and he postulated a law that says that when a body is wholly means totally or partially, that is partly, not all, not totally, immersed in water, comma, it experiences an upward force. It experiences an upward force called upthrust, which is equal in magnitude to the weight of the water displaced, which is equal to the weight of the water displaced. Does that make sense? So, I'm going to explain this. Now, it says that when a body is wholly or partially immersed in water, that is, a body that is going into the water or partly immersed in water, it did not totally enter into the water. When that body goes into the water, it immediately experiences a force upward. So if I have a container like this, and it's filled and water is inside, if I drop this ball inside, for example, the moment the ball begins to enter into the water, and it finally makes its way into the water, it's going to experience an upward force that is called upthrust. So this upward force is called what? Upthrust, denoted by U in most cases. That upthrust will be equal in magnitude to the weight of the water that is displaced. So that day in the laboratory, Archimedes and I were in the laboratory and we were trying to experiment. What we used was a Eureka can. That's on the lighter mode anyway. We used a Eureka can. So basically, we create a Eureka can is just a tube that looks like this. Normal container, but there's a space here for water to leak. So these were our buckets. Now, so the moment this ball got into the water that day, then we put another ball here to measure the amount of water that will drop. You of course know, if you fill a bucket of water to the brim, you fill it to the brim, if you put something else inside, what will happen is that some water will spill. So that water that spills will have equal volume as the body that entered that water. Let me take that again. The water that got spilled out of this thing, the moment this guy began to enter into the water, that water that got spilled out is going to be equal in volume to the body that entered the water. So the volume of the body will be equal to the volume of the water that spilled away. So basically, in his principle of flotation, the same guy, I told him to state it too. In his principle of flotation, I said that he said that if a body must float in water, it must displace its own what? Its own volume. Do you understand now? It must displace its own volume. Is that okay? So some water will spill over or will give way for its own volume to be contained in that water. So that volume that is contained in water is going to be what? The volume of the object. Okay. Now I believe that is clear. Now also, you know that since this is the volume of the water, it is also such that when you weigh this water, this amount of water, which is equal in volume to this guy, if you weigh the weight of the water at the end of the day that spills, don't forget, it is the weight of the water that spills that you will measure, and you will find out that it is going to be equal to the upthrust that this guy experiences. So what is upthrust? Let me tell you what upthrust is. So water is displaced here, right? So water is displaced here. It means that upthrust, which we said, will be equal to the what? The weight of water displaced. Weight of water displaced, or we call it loss in weight. Now this is it. Listen to me. Let me explain this loss in weight. If you ever try to draw water from the well, you are going to notice that by the time the fetcher is into the well and inside the water in the well, you will notice that at the time you are drawing the well, you'll be telling your friend, Ashebi, you say that this thing is heavy. Is this one heavy? Is this one heavy? This one I'm drawing out. By the time the fetcher makes its way out, just out of the water, and then you now begin to draw. You know, you're saying that, show is this that is heavy. Is this thing that is heavy? The moment it just makes you out of water. Where is hanging this? Where is hanging this? What is drawing it? Yeah, it has become heavier because now you are beginning to feel the actual weight of this Baba. Do you understand me? You are beginning to feel the actual weight of the fetcher because it has made its way out of the water, and now the real weight, which is weight that is due to association with gravity, or you say weight that is actually having. Now, the reason why when it was inside the water, you couldn't feel the entire weight and you're telling your friend that is this one heavy, is this one heavy, was because there was an upward force known as what? Upthrust, that led to a loss in weight. And that loss in weight is the weight of the water that it displaces when it's inside that container. Does that make sense to you now? Okay. So don't forget that the upthrust is the loss in weight that it experiences. So it is such that the upthrust of a body is going to be, or the upthrust on a body that is acting on the body, that is acting upward on that body, is going to be the weight of the substance in air, which is the actual weight of the body, minus the weight in any liquid that it is put in. Don't forget that. Don't forget that. So the upthrust force, like fuse, is going to be the weight of the body in air normally, minus the weight of its weight inside the liquid. Because it will experience a loss in weight in any liquid you put it. Anybody. Is that okay? Alright. Now let's go. So, and it's such that for a body to also float in water, in a liquid, it must be less dense than the liquid. The moment that body is denser than the liquid, it will sink. Does that make sense to you? If a body is denser than the liquid, it will sink in that liquid. All right, let's go on now. So we have established that upthrust, right? So we have two formulas now that we have derived. So we have derived one rather. Let's derive the second one, upthrust. We said upthrust is what? The loss in weight of the body. And we said this loss in weight is equal to the weight in what? Is equal to what? The weight of water displaced. Does that make sense to you now? Weight of water displaced. Not the water inside the well or inside the container. The water that body makes to give way. Is that okay? Alright. So now, what is the weight of the water displaced? Now listen. You remember that weight of water displaced will be mass of water times acceleration due to gravity. Am I clear on this? This weight is mg. Does that make sense? Okay. If that makes sense, then remember that density of a material, say for example, density of water that we already know to be 1000 kilograms per meter cube, is equal to the mass of water over what? Volume of water. So it therefore means that mass here can also be represented by, if I cross multiply, m sub w will be equal to what? Rho w v w. Is that okay? So we have that this will be the mass of water, rho w times vw. So I can represent that here and say that it will be rho w times v now times g. Now listen, this is where the problem is. Now you see, this density will be the density of water, of the substance of the liquid, because different liquid have different densities. So the upthrust that a body will experience inside it is dependent on the density of the liquid. If the liquid has different density, it will experience a different upthrust than if it were in water. Does that make sense to you? The upthrust that the body, the upward force that the body experiences, or the loss in weight, are you seeing I'm using an interchange so that you get it? The loss in weight or the weight of liquid displaced that the body experiences, basically upthrust, that the body experiences in the liquid is dependent on the density of that liquid. Is that okay? So the denser the liquid, the higher the, no, let's do that for now. Now my point is this, that the density, the upthrust that a body experiences depends on the density of the liquid. Then it now also depends on the volume of the object. Wait, calm down. This volume we said was V sub W. Do you remember? What is this V sub W? It is volume of what? Water displaced. So is it that we say that it is density of the liquid itself times the volume of water displaced or volume of liquid displaced? Any liquid. So it will be density of the liquid times the volume of water displaced or liquid displaced. It has to be that, liquid displaced. And remember that the volume of liquid displaced is equal to the volume of the body itself, because if the body floats in water, its own volume in amount of water will give way, right? That amount of water that gives way is equal to the volume of the object. Yeah? Okay, if that is the case, then it means that this volume is also going to be the volume of the object. So the upthrust is going to be what? The density of the liquid times the volume of the object, or the volume of the water or liquid displaced times acceleration due to gravity. Don't forget this. Okay, so we have four formulas. What are three formulas rather? What are three formulas? Density is equal to mass over volume. Upthrust is equal to weight in air minus weight in liquid or weight in water. And upthrust is equal to what? Rho L V G. Okay. Now let's move on. Let's go on to what is called a phenomenon called relative density. And this is one of the ones that gives students problems the most, and it's the simplest thing in this world. It's simpler than ET. I promise you. I promise you. By the time I finish teaching in the name of Jesus, and you don't still understand it more than ET, then don't blame Alpha. All right. So let's talk about relative density. Relative density. It is also called specific gravity. One thing you should know about this is that this guy does not have a unit. I've mentioned that in the video. Make sure you watch that 3 hours video. Now, what is relative density? It's basically, we're going to write it based on the formulas. Yeah, okay? So relative density is just relative. When you call something relative, it means you are comparing two things. Okay, so relative density is going to be the density of a substance. So let's talk about relative density of first of solids. It's going to be the density of that solid over density of water. Or let me show you writing all these formulas down. Or the mass of that solid over the mass of equal volume of water. The mass of equal volume of water. Now let me analyze what this means. Equal volume of water means that the volume is going to be equal volume with the solid. So since that guy is similar, then let's compare their masses. That will be the relative density of that solid. Does that make sense? Since the volume, which will be the you know that rho is equal to mass over volume. So since the volume is equal, so because it's mass of equal volume of water, that, and it's going to be the mass of, this mass of equal volume of water is going to be the mass of the water that is displaced. Does that make sense? So that means that it's going to be, we are going to now be comparing the mass of that solid to the mass of water, since they have equal volume. Does that make sense? Okay. Another one is the weight. Since mass can be compared, then we also see that weight of what? Of the solid over the weight of equal volume of water. It has to be weight of equal volume of water again. Another formula is the weight of the substance in air. Weight of solid again in air over, what is the weight of equal volume of water? It's the upthrust that is experienced. Do you remember? We said the loss in weight is going to be equal to the weight of the water that is displaced. You remember that, right? So weight of equal volume of water is equal to the upthrust in water. So that loss in weight is equal to the weight of the volume of water that is displaced. Okay. So we have all these formulas for one thing. Do you understand now? All right. Then the last set is relative density of liquid. Now the reason why this guy has no unit is because you notice that all the denominator and numerators have the same unit, so they always cancel out. Okay. So relative density of liquid is just, it's very simple also. Usually in your exam you'll be tested with a liquid and water, a liquid and water. So for example, we want to do this. Now relative density of a liquid is going to be the weight of a substance in that liquid relative to the weight of the substance of a particular substance. You are going to be using a solid to immerse in a particular liquid and immerse that same solid in water, so that you know the weight of the substance in that liquid over the weight of substance in water, or the upthrust that thing experiences, that solid experiences in a liquid, to the upthrust that it experiences in water. In the upthrust you experience in water, yes. And of course, another formula is, so those are the two formulas that you can use for weight, for relative density of liquid. When we solve questions, it's going to be clearer to you. So let's solve the first question. The first question says, the first question says, an object weighs 12 Newton in air. So once you read like that, I've told you the best way to calculate things like this in physics is the heuristic approach of writing all your parameters first. So go like this. An object weighs 12 Newton in air. You say stop. Then you now go and write 12 Newton in air, right? So weight in air is what? 12 Newton. And I say continue. And 8 Newton in water. I say stop again. 8 Newton in water. So it's a weight in water is what? 8 Newton. Now, what is its weight when immersed in a liquid of relative density? This. Now, you saw these two parameters. Before you read the final question, there's something you can first do. You have weight in water, weight in air. Okay, then it means that if it's weighing less in water, then it means that it has experienced what? Loss in weight, right? Which is what? Upthrust. So the upthrust is going to be what? The weight in air minus weight in water. That's going to be what? 12 minus 8, which is equal to what? 4 Newton. So this is the loss in its weight when it is inside water. 4 Newton. Does that make sense? It now says, what is its weight when immersed in a liquid of relative density 1.5? So a liquid has relative density 1.5. RD of a liquid is 1.5, okay? Now you remember that relative density of liquid is equal to what? Upthrust of a body in water. So we have to calculate its weight when immersed in that liquid, in this liquid, right? Okay, it's going to be the weight of the body in the upthrust of the body in that liquid over the upthrust that it experiences in water. You remember that formula? I gave you that formula. So relative density of the liquid is going to be 1.5, which is equal to the upthrust in that liquid, which we don't know yet, over the upthrust in water is what? 4 Newton. By the time you calculate the cross multiply, you're going to have U sub L is equal to 1.5 times 4, which is what? 66. So that will be 6 Newton. Now, 6 Newton is going to be the upthrust that body will experience in the liquid. Okay, it now says what is its weight when it is immersed in that liquid. Remember that this upthrust is going to be its weight in air minus its weight in that liquid. Does that make sense? Such as we did here. Okay, so this upthrust, which is giving us 6 Newton, 6 is equal to the weight in air, which is 12, minus the actual weight in that liquid, which is what we're looking for. So by the time you do your maths, you're going to have that. Let me clean this part. This guy here, W sub L, this guy comes there, this guy goes there. So this W sub L is what? 12 minus 6, which is equal to what? 6 Newton. And that is the answer. That is the weight of the guy in the liquid. Does that make sense? Let's go to number 2. The mass of a specific gravity bottle is 15.2. You say, shut up. You go. Mass, now, specific gravity, we said is relative density, right? Or relative density bottle. So the mass of that specific gravity bottle, you say, M sub G, that's mass of specific gravity bottle, is what? 15.2 grams. Okay? When it is empty, now you don't need to convert if you are not giving differing units. If you're giving differing units, let's say 1 kilogram, that's when you need to convert. Everything is grams, so you can leave it. When it is empty, so its normal weight its normal mass is what? 15.2. So it is 24.8 when filled with kerosene. So the mass of that thing plus when you fill it with kerosene, this 24.8 is going to be the mass of the guy plus the mass of kerosene. So that becomes what? 15.2 plus a particular guy to give us that what? 24.8. So by the time you work your mass, x will be equal to what? 24.8 minus 15.2. That becomes 9, yeah? That becomes 9.6. So we have x is 9.6. What is x? M sub k. So the mass of kerosene is what? 9.6. Are you seeing what I'm doing? Now, and 27.2 when filled with distilled water. Okay, the same way you did that, if you fill it with distilled water, the weight you will get or the mass you will get will be the mass of the guy plus the mass of distilled water, and that becomes that our 15.2 plus a particular mass of distilled water will give you what? 27.2. Okay, so you now say that M sub W what? 27.2 minus 15.2, and that gives you what? 27.2, 15.2, you have 0, 2, 1. That will be 12. So is equal to M sub W, that's mass of distilled water is what? 12.0 or 12 grams. Are we good with that? It now says calculate the relative density of kerosene. So how do you calculate the relative density of kerosene? Now, what do you have here? You have the mass of kerosene and you have the mass of water. Now, keep in mind, another formula for relative density is also the mass of a liquid over the mass of equal volume of water, which is what we did, yeah? Okay, so why is that so? Because why is it equal volume here? Are we giving volume here? No, specific gravity bottle, both of them will fill that thing, so they will occupy the same volume. Does that make sense now? So it's going to be, RD is going to be the mass of that substance, which is N96 over 9.6 rather, over the mass of equal volume of water, which will be 12. Does that make sense? So, and if you do your maths, you're going to have, what can I cut here? 8. 96 divided by 8. That is 1 to 1.2. 120 divided by 8. 120 divided by 8. Okay, 12 can even go. So 12 here, 8. So 1.2, that's 12. 12 here, 0.8. 12 here, 10. 0.8. Oh, okay, it's not 120, that's 1. So 0.8. So relative density is got to what? 0.8. And that's the answer. No unit. I hope that is clear. Now, this one says a block of material of volume this. You go like that. The block of material has this volume. Volume of block is what? 2 times 10 raised to the power minus 5 meters cubed. Right first. And density that, stop. So the density of the guy is what? 2.5 by 10 to the third kilograms per meter cube. Okay? Now, once you have these two parameters for a particular material, for the same material, you can do the third, which is what? The mass of the block. And the mass of the block of what? This times this, basically, from rho equal to m over v. So mass will go to what? Volume times density. So you have what? 2 times 2.5 times 10 raised to the power minus 5 times 10 raised to the power 8 power 3. What I just did is, I multiply this by this and this by this. Is that okay? So this will give me 2.5 times 5 times 2, that's 5. Times 10 to the power minus 5 So minus 5 plus 3, that becomes 5 times 10 to the power 2. This is going to be the mass of the block. Is that okay? Now it says a block of iron density this is suspended from a spring balance. So a spring balance is suspending it, and half of its volume so sorry, thank you. This is going to be minus 2. So the mass of this guy, sorry, minus 5 plus 2, that's minus 2, thank you. So it says that it's suspended from a spring balance with half the volume of the block immersed in water. So half the volume of the block is immersed in water. Let me show you what that is. So inside this water now, so there is only half of the volume of that block is immersed in water, not the total volume. So some parts are still up above the water. Is that okay? So half of its volume is immersed in water. Okay, let's make sense of that. If half of its volume is immersed in water, then it means that the volume of water that, since actually Archimedes' principle says that when a body is only partially immersed in water, is a kind of thrust which is equal to the weight of the water displaced. And we said that for a body to float in water, it will displace its own volume. So when a body enters water, it displaces its own volume. So it means that if not the complete thing entered water, if only half of it entered water, it means it displaces half of its volume. That makes sense. So it means that volume of the water that is displaced is going to be half of the volume of the guy. And the volume of the guy is this guy. So times 2 by 10 to the minus 5. So this takes care of this, and we have V sub W is equal to 1 times 10 to the minus 5. So this is the volume of water displaced. Okay. Now, it now says it's suspended from a spring balance with half of its volume of the block immersed in water. What is the reading of the spring balance? Okay, now let me ask you this. What do you think the reading of the spring balance will be? The reading of spring balance is going to be the weight in water, isn't it? Not the upthrust. The upthrust cannot be calculated by the spring balance. It's the weight in water. So to get that, it means that we have to subtract the weight in air. We subtract upthrust from it to get the weight in water. But we have not gotten anything that looks like upthrust here. So let's make sense of this whole information. We are given that density of water is this. Okay. So with that, we can find the mass of this water that is displaced. Since the volume of this water that is displaced is half of the volume of that guy, so the density of this water that is displaced has been given to 1000 kg per meter cube. That one is constant. But the mass of this guy will now be what? This times this. So we have 1000 times 1 by 10 to the minus 5. This makes sense, yeah? So that will be 3 again minus this. Then we have mass of water is what? Mass of water is going to be 1 times 10 to the power minus 2. I'm trying to avoid mistake. Okay. Now, in order to find density, upthrust, we need weight. So let's calculate the weight of the block from the mass of the block. Weight of the block, what? Mass of the block times acceleration to the gravity. Weight is mg. So mass of the block is what? This guy. That will be 5 times 10 to the minus 2 times 10. We are giving that here. Acceleration to the gravity. So this takes care of 1 here. Then we have what? 5 times 10 to the power minus 1, which is 0.5 Newton. So this is the weight of the block in where? In air. Now, what is now the weight of the water? So the weight of the water displaced. Weight of the water displaced that has equal volume of half of that guy. Okay, it's going to be what? 1 times 10 to the power minus 2 times 10. It's going to be what? 1 times 10 to the power minus 1, which is what? 0.1 Newton. This makes sense. Yes. Okay. If that's the case, so this is the weight of the water displaced. So this is going to be the upthrust of the water. Remember, the weight of the water displaced is the loss in weight or the upthrust. Okay, so I recall that W sub A, upthrust is going to be W sub A, weight in water minus weight in air minus weight in water. Now we're looking for weight in water now. Okay, and W sub W here is going to be the upthrust. Does that make sense? Not this one is weight in water, this one is weight of water displaced. Is that okay? So U, which is upthrust here, is going to be 0.1 Newton. So 0.1 is equal to weight in air is 0.5 Newton minus weight in water. Weight in water is the weight that the spring balance will read. So this guy will come here, this guy will go there. So weight in water is going to be 0.5 minus 0.1. That what? 0.4 Newton. I hope that is clear. All right, let's attend the last two questions. This one says, if a spherical bulb, so take note of the shape. Whenever you see shapes here like this, they are likely to ask you about the volume of the shape. Of a spherical metal bulb of radius 3 centimeter is fully immersed in a cylinder containing water. Okay, so let's write that. He said the radius of the metal bulb is what? The radius is 3 centimeters. Now you don't really need to convert if all the units are equal. And if you check your options too, it's given in centimeters, you don't need to convert to meters. So in a cylinder containing water, and the water rises by this. So the water rises by this means that, so if you have a cylinder, if you say the water rises by 1 centimeter, it means the height of the water increased by 1 centimeter. For the height to increase by 1 centimeter, it means the volume has increased too. So it says, what is the radius of the cylinder? So let's go again. If a spherical bulb of this radius is fully immersed in a cylinder containing water, by the time you immerse it in the water containing water, just see, to solve density questions, just try and understand it. Okay, if you immerse it in cylinder containing water, what will first happen? It will displace its own volume, right? Okay, so it means that rise in volume of that guy is going to be the volume of the bulb. Does that make sense now? Because the increase in volume, or should be, if the thing was to the brim, that volume by which it flows should actually spill. Does that make sense now? So first let's get the volume of the bulb, because it's the radius. And volume of sphere is equal to, let me the formula for volume of sphere, 3/4 pi r cube. I don't forget this. Am I correct? Okay, all right. I just needed to confirm. So you must know maths. Is that okay? You must know maths. The volume of the sphere is going to be this. So that becomes 3/4 times pi times, we're not giving pi here, so we'll retain pi. We're not giving the value of pi, so we'll retain pi in our calculation, times r cube, and r is 3, so that'll be 3 times 3 times 3. So by the time you solve this, you're going to get 3 times 3 times 3. 3 times 3, that's 27. So that'll be 27/4 pi. Is that okay? Let's work with it this way. This will be the volume of the, you see you're doing like say this formula not correct. This guy is 81, I'm sorry. 3 times 3 times 3, that's 3 times 3, 3 times 3, 9, 9 times 3 times 7, 27 times 3, 81/4 pi, okay? Now, this is the volume of the bulb. So the volume of the water that rolls is going to be equal to this. This is volume of bulb, which will be equal to the volume of water that rolls up. Does that make sense? In other words, what is the radius of the cylinder? Okay, recall that this volume, 81/4 pi, will be equal to the volume of cylinder. What's the volume of cylinder? Volume of cylinder is given by pi r squared h. Okay, so this guy, this value here is going to be equal to, because it's the volume of the bulb, does that make sense? So which will be the rise in volume in water, rise in volume of water there, okay, which will be pi r squared h. So that will be pi times r, which we are looking for, squared h now. Oh, see, so this is what we'll do now. Let's recast that so that okay. Either ways, we're gonna have pi takes care of pi. Height, okay, height is given here. It rises by 1 meter. We didn't write that. So it rises by 1 centimeter. So h is 1 centimeter. So times 1 centimeter. So we now have 81/4 is equal to r squared. Take square root of both sides. So square root of this. Then square root of this and this is going to be equal to square root of this is 9 over square root of this is 2. So the answer is 9/2 centimeters. That's going to be the radius of the cylinder. Now let me try to explain it. It says that spherical metal ball has this radius. So let's calculate the volume. And please verify in the comment section. Let me know if this formula for volume is correct. Is that okay? Now, if that formula is correct, then this will be the volume of the sphere. And that volume of the sphere, because that sphere is immersed in water, it will displace its own volume. So the volume of the sphere will be the volume of the water that it displaces or that rises. And that water, the height of the volume that rose was 1 centimeter. So this volume should be equal to this. And then when you solve, you get that centimeter. The last, all right, let's go to number 5. Okay, in order to assist you so that it doesn't look like I'm going to solve the entire question, solve number 5 and drop the answer in the comment section. I'm going to give you the correct answer. I'm going to let you know if you are correct. Is that okay? I'm going to let you know if you are correct. So you first to let me know that you watch the video till the end. Solve this question and drop the answer in the comment section. And also do what to subscribe to the channel and click the bell notification so that you'll be notified whenever I drop a new video. God bless you as usual. And I wish you success in your exam. God bless you.